Welcome everybody. Okay, welcome everybody to the number theory section. This is our final day. And we have this wonderful lineup of speakers. We start the section with Professor Marc Hindry, my good friend from Paris 7. And Marc's a good friend of Brazil. He's been here teaching us algebraic geometry and arithmetic geometry and number theory for many years, and we are very grateful for him. He's been in University of Brasilia many times also. So he's a good friend of us. And he's going to talk today about integral points on a family of elliptic curves. Thank you, Marc, for accepting this invitation.
Ok, thank you, Emma. So, obrigado pelo convite e, bom, gostaria de estar em Brasília com vocês, mas vou ficar aqui em Paris falando em inglês.
Okay.
So the topic is integral points on a family of elliptic curves. So it's a work that actually it's almost finished with Emma and Diego. So I will perhaps first give the plan. Oh, how do I? Okay. So sorry, I will give the plan of the talk. So the beginning is a very classical number theory problem that was suggested by Mordell in the 60s. There was subsequent work by Emma Godinho-Porto-Togbé and then Lee-Louboutin. So all this work with essentially algebraic number theory, factorization in Dedekind domains. So we'll propose a different approach to the same problem via the theory of elliptic curves. So then we'll get a nice theorem on the family of curves we're going to look at. I will discuss then exceptions to the theorems. And then the last parts are a very brief sketch of proof of the results. So let's start with the element. So high school. So we give out a natural integer, a. So a will be 1, 2, 3, etc. And we ask which numbers can we write, both as a product of 2 consecutive integers and as a product of 3 natural numbers in arithmetic progression with common difference a. So there's 2 ways to write the equation. The first one is you write capital N is n times n plus 1. And also m plus a, m plus 2a. So as I already mentioned, the problem has been addressed as a problem in algebraic number theory, but we will propose another approach via the theory of elliptic curves. So for elliptic curves, it's more convenient to write the equation y squared plus y equals x cubed minus a squared x. This is a so-called Weierstrass equation for the elliptic curves. And in that case, we look at the integral points. Of course, the solution with x, y integral. Of course, we'll allow them to be negative, which is a bit different from the original problem, but it's quite natural. So for given A, Ziegel's theorem tells us that the number of solutions is finite. It's important to have this in mind. We will see that actually the set of solutions is never empty. There's always integral points. The other thing is that there are efficient algorithms to compute a given A. So let's say I give myself a value A equals 17. I can ask the computer to compute the integral points. So the point is to have, in some sense, general theory for it. So the first result, as I already mentioned, is due to Mordell. So that's for A equals 1. That the only solution is what the other one is 2 times 3 and 1 times 2, 3. And there is another less obvious solution, 210. More importantly, it's not at all trivial that these are the only solutions. It's really a paper that takes something like 15 pages to prove. The next work was done by Godinho-Porto-Togbé. So what they showed, they solved the problem for A equals 2 and A equals 5. Now there's a different feature for A equals 2. There are 3 solutions, so 3 integers that can be written as product of consecutive integers. And for A equals 5, there are actually 5 solutions. You also note that the solutions, the last ones, are very large. I mean, they would be difficult to find if you just do a random search, a systematic search. It would be difficult to find them. I won't say much about the proof. Essentially, the essential point is that the ring of integers, when you add the solution, so you get a real cubic field, and the ring of integers is a UFD domain, and you have to determine the group of units. The point is that these are the only values of A for which this domain is UFD. The next paper is by Lee and Lee-Louboutin. They have, I think, 2 interesting results. Well, the first one, as I mentioned already, is that there are always solutions. Well, they give explicitly 3 solutions. So you notice that for A, solutions, the first one is 0, so it doesn't count for the original problem. So we always get 3 solutions, and this, well, it's easy to check that those formula give a solution. That's not difficult. What was difficult was to find these solutions. I honestly have no idea how they found them. I will give a geometric explanation for this solution, but it comes from elliptic curves. The geometric explanation comes from elliptic curves, not from the theory of factorization. So first we have, so it's always 3 solutions. And then in the condition, they prove that they are the only solutions. So the 2 conditions are, well, you need the class number of the field to be odd. So that's a weaker condition, of course, that the previous one, which was asking that the class number should be 1. And the other solution is that the discriminant, this discriminant will be the discriminant of the elliptic curve, but here it's the main factor of the discriminant of the cubic field. It should be square free. And then they prove that there are only 3 solutions, but which is quite a nice result. So it works. I've given the list that's in the paper. It works for 20 values between 2 and 200. I have given the list. It is, well, it gives more or less for 10% of the values, it gives the solutions. You notice that the number 5 is outside this, this criterion because the discriminant has a square factor. So the Lee-Louboutin theorem doesn't apply. And you notice that there are 2 extra solutions, so it cannot apply. So I will well, briefly discuss what is the arithmetic of this cubic field that all this paper look at. So there's a slight shift of parameter. I've just multiplied by 2 because it's easier to write, but it's the same cubic field. So you take the root of the equation, x cubed minus 4a. So there is an x missing here. It's 4a2x plus 2. So you can compute the discriminant. So the well, the discriminant you factor. There's a square full part and a square free part. And from that, you can sort of deduce many things on the arithmetic of the cubic field. For example, the ring generated by theta is not, in general, the full ring of integer. The index is exactly this factor that appears to a square. And then the discriminant of the cubic field is essentially M1. The 2 and 3 parts are trivial. It is also possible to find two generic units. I have written the formulas, which won't be important in what follows. The important thing is that they are independent, at least if A is bigger than 1. And so you find they are relatively small. I mean, so you find that the regulator of the number field is, well, small. It's a power of log A, or smaller than the power of log A. So if you apply the Browse-Eagles theorem, which is entirely effective in the case of cubic fields, well, you find a lower bound for you find a very good estimate in some sense for the class number times the regulator. So if you, since you know you have a bound for the regulator, you deduce that the class number should be large. I mean, should be, it is bigger than square root of M1 over log M1 log A square. So if, for example, you take the Lee-Louboutin hypothesis, there's no square factor, then actually the class number grows like A cube. So you will never find again class number 1. And in some sense, odd class number becomes rarer and rarer. So that's about all I will say about the arithmetic. I will come back to this cubic fields a bit later. So now I want to go to elliptic curves, which is the main topic of this talk. So we rephrase the problem as finding integral points on the curve with the equation that I have written again, and this time I have not forgotten the x. So this trivial remarks is that, well, there is a group on the set of rational points, but for example, the inverse -1 multiplication by -1 preserves integral points. So integral points always come in pairs. That is, you have a y that's positive and a y that's negative. Essentially, that's what it's safe for. Essentially, we'll consider those as the same point. The other trivial observation is that there are obvious points on these elliptic curves. I mean, you take y equals 0 and x equals 0, a or -a. So this gives us what I will call trivial integral points, those 3. Now, the point is that, of course, those points, they generate a group. So the integer points are not stable under the addition law, of course, only rational points. But what happens is that in this case, when you compute the double of those trivial points, you get integral points, which I will call standard integral points. Now, if you remember more or less the formula of Lee-Louboutin, that's exactly, of course, the 3 solutions that were found by Lee and Louboutin. So it's not new. What is new is a geometric interpretation that I find quite nice. I mean, if you, from the point of view of elliptic curves, you find naturally those solutions. And again, I really don't know how they found, if it was by computer search or some other trick. Now, if we start studying the elliptic curves, so there are 2 remarks, others that are a bit more complicated. The first one is that the sum of the trivial points is 0 because they lie on a line. I think I haven't read the line, but I guess you know how is defined the group law on an elliptic curve on a cubic. well, 3 points sum to 0 if they are on the same line. So the group generated by P1, P2, P3 is also generated by P1 and P2. So let's start by special cases. If I put A equals 0, which after all is allowed, then it's essentially the Fermat's theorem for cubes, that there are 3 rational points. And so the group is Z over 3Z. We will use that later when we will say that when we reduce modulo A, our elliptic curve, we get, of course, this group Z over 3Z. Another observation is that A 1 or bigger, then the torsion group in the group of rational points is always trivial. So that's not so easy, but not so difficult. I skipped the proof. The other statement is that, well, for A equals 1 is a bit special. We have that the group generated by the trivial points is cyclic, well, is monogeneous or cyclic. It's generated by P1. In fact, we have the relation that P2 is twice P1 and P3 is minus 3 P1. Now, for all A greater than 2, there's no such relations. And in fact, the point P1 and P2 are independent. So we prove that the group of the trivial T for trivial, the trivial subgroup is a group of rank 2 generated by P1 and P2. So that's for rational points. So remember this group T because it will play an important role. So an elliptic curve, we want to compute a few of the invariants. So one is the discriminant, the minimal discriminant of an elliptic curve in a sense. So when we compute it, we find this, which is what essentially the discriminant of the cubic field we were looking at. Also important is the J invariant. So I recall that two elliptic curves that are isomorphic, of course, have the same J invariant. Now, if two elliptic curves have the same J invariant, they are isomorphic over the algebraic closure of the field, not necessarily over the field itself. But here, what I want to point out is that when A becomes large and large, and at some point we will assume A large to prove things, then this J invariant, of course, it's obvious on the formula, tends to 1728. And that is the J invariant of this well-known CM elliptic curve, which I have written the equation downstairs. It's y squared equals x cubed minus x. And in some sense, if you look at the equation and rescale it, you can see that the point P1, P2, and P3, they tend to the two torsion points on the curve at infinity. This will be important in the last part of the proof of the main theorem. Now I come to the main theorem. That I come back to the initial problem. So trying to find all the integral points on these elliptic curves. So the theorem says, so we've already seen that for A at least 2, the rank of the elliptic curve is always at least 2. Now what the theorem says is that you have an exception, that's A equals 5. And if the rank is equal to 2, and I will explain on the next slide what mildly square 4 means. It means this gamma A is not too large. So essentially it says that you don't have an absurd huge factor with some exponent in the determinant. So it's something that actually should be always true, though we don't know how to prove it. It's implied by the ABC conjecture, for example. So what the theorem says is that if the rank is 2 plus a very mild hypothesis, then the only integral points are the one we already know. I mean, we already know the three trivial ones and the doubles. And what it says is that these are the only ones. When you look at the values A to compare to do the comparison with Lee-Louboutin criterion, well, first you will notice that, well, I've written the list between 2 and 200. The criterion applies to all these numbers. So the numbers in black are those which were already appearing in Lee-Louboutin. And the number in green are the new numbers for which we can prove the same result. So it applies for 52 values, so something like 26% of the values of A, which is better, of course, than 10%. You notice also that there's one exception. It's for A equals 5. The rank is 2, but there are 2 extra integral points, as I already pointed out. So I will give just a bit later an explanation for that. So this is the main theorem. I like this theorem because in some sense, not only it's better than Lee-Louboutin, but also, as I will explain, I think it really explains the matter of things. I mean, it will be very difficult to improve this, this statement. So now I explain a little bit, I define precisely what I mean by mine Lie square 4. So I will define this invariant gamma A, and perhaps I remind you that the theorem is that if gamma A is not too large, then everything works fine. So I've taken the value 0.35. It's not the best value we can obtain, but at least it's bigger than 1/3. I will explain why it's nice that we can take it bigger than 1/3. So how do we define this invariant? Well, I look at the discriminant. I take away the power of 3. I mean, there's a trivial power of 3, which is 0 if A is not divisible by 3, and the exponent is 3 if 3 divides A. So I take out this. Then I separate the discriminant into a part that is 2 parts that are coprime. I take all the factors that appears with exponent 1, that gives me a delta 1, and I take all the prime factors with a bigger exponent, and that builds up my delta 2. So for a square free, this gamma will be 0. So, and the definition of gamma is log of delta 2 over log of delta. So it's between 0 and 1. So to have a better grasp, how large can it be? Well, it's not difficult to show that you can get gammas that are almost 1/3. I give the solution. I mean, you pick up a Pell-Fermat equation like 4a squared minus 13b squared equals 3. So I have chosen 13, of course, so that there are solutions. So if there are solutions, there's infinitely many. And then there's a big square in the discriminant. And if you work this out, you will see that the gamma A is it's at least 1/3 essentially. Now this gamma A is very often 0 because there's lots of square free values, approximately 93%. That's statistical, and there's a very reasonable conjecture which would imply this, but it's not a theorem that the proportion is 93%. Now, the ABC conjecture, if you believe in it, will imply that essentially gamma A is smaller than 1/3. That's why I liked to be able to choose gamma naught equals 0.35. And the biggest for A smaller than 400 is 0.31. So it's actually one of those numbers. So that's to give an idea that this hypothesis is very mild. I mean, essentially it satisfies for all numbers, even if we cannot prove it. Now, I will decompose the proof of theorem A into two theorems. And there are, of course, theorem A has hypotheses on A. Theorem B and C have essentially no hypothesis. So theorem B, what it says is that, well, if we look at integral points that are only in the group, the subgroup generated by the trivial points, then we find only the points that we already know. That is the standard points. So this holds for all A. It holds also for A equals 1, for A equals 5, that are a bit exceptional. Okay, the way we prove it, I mean, we'll prove it actually for A large enough, and then we need to do a computer search to check that the conditions are still satisfied for small A's. Well, A's that are not so small, but only a finite number of them need to be checked. Theorem C is a bit different. What it says is that, well, I look at the subgroup generated by the trivial points. Now, then it might be divisible. So I take the saturation. The saturation is what I call this T bar. Is the subgroup of points such that a multiple lands in T. Now, under mild assumption, what we prove is that this T bar is equal to T. With one exception, A equals 5. 5 actually is 2. And this is the explanation from the elliptic curve point of view. It's the explanation of the two extra solutions that Emma and co-workers had found. So as more or less a trivial corollary of theorem C, you find that if A is not 5 and gamma is not too large, the rank equals 2 means that actually the group of rational points is exactly the group generated by the trivial points. So it's an easy corollary from theorem C. And I hope it's more or less obvious now that theorem B and the corollary imply the main theorem that I stated. I mean, if you have the two conditions that the rank is 2 and gamma is not too large, then the group of rational points is the group generated by the trivial points. That's by theorem C. And by theorem B, we know the integral points in T are exactly the expected ones. So of course, the problem now is to explain how we prove those two theorems. It's by very different argument. So before that, I will briefly come back to the full factorization approach of Mordell and followers. The link between the theory of elliptic curves and this cubic field analysis can be given by what is called the two descent. So the two descent is a classical algebraic device that initially is made to compute the rank of an elliptic curve. So we define the following map. I remind you that theta is the root, so I've written it again, and this time I have not forgotten the x. So theta is the root of x cubed minus 4a square x plus 2, and theta generates a cubic real field that I call L. So we define the map from the rational points of the curve to, the quotient of multiplicative group of L modulo squares. The map is very simple to define. To a point Q, we associate well, the coordinate, the x coordinate of q minus theta over 2, so modulo squares, because we want to land in this small group. So it is well defined because, well, theta is irrational, so this xq minus theta over 2 is never 0. The wonderful thing is that it is a group homomorphism. That's not that part is not obvious, and also that the kernel is exactly made of the doubles of points. So this is essentially the theory of the two descent. So we look at this map, and well, this way we will get bound on the rank of EA of Q, if we can bound the image. So I have another observation is that I have numbered the 2 units that I quoted earlier exactly so that the image of my first trivial point is exactly the first unit, and the image of the second point is exactly the second unit, modulo squares, of course. So the image of the trivial subgroup is essentially not the group of units, but the, the group generated by epsilon1 and epsilon2. So modulo square, actually, most of the time, it is the same as the group generated by units. Now, this this L star modulo square is not a finite group, of course. I mean, Q multiplicative of group of Q modulo squares is not at all a finite group. So we want to cut down the size to a finite group. And again, the two descent does this for us. So I give explicitly the definition of the subgroup, the finite subgroup that will contain the image. So it is a subgroup that, well, you have to define the place, the set of place S, such that the order of the discriminant is positive and even. You take places, you don't look at places above 3 and 2. You forget about. Well, you ask for alpha to have an even order at all V that's not in S, and to have a strictly positive norm. Now, if you do that, well, it's pretty obvious that this group is finite. And we can actually compute its cardinality. Essentially, you have, well, you have a 2 that comes from the units, you have the number of places of S, and you have also the 2 parts of the idle class group. It's even the idle class group of the S integers, but I will forget the S afterwards. So the main point is that the image of E modulo 2E is inside this finite group. So if we have this in mind, we find this proposition where, well, I have introduced the Tate-Shafarevich group that I won't use again because it actually gives some more information on the elliptic curve. So if you know about the Tate-Shafarevich group, it's interesting. Otherwise, you forget it. I will not use it again. So this analysis proves that the rank plus actually this dimension of this mysterious group is smaller than the dimension of the 2 part of the class group. Little s. So little s is a number, have I written it? Yeah, the number of primes whose exponent is positive and even. So, well, this allows a nice comparison. I mean, if you look at Lee-Louboutin hypothesis, well, they assume that the class number is odd, so the dimension of the 2 parts is 0 of the class group, and they assume something stronger, but they assume S equals 0. So you see that in the Lee-Louboutin conditions, you automatically get rank equals 2. So actually, our theorem applies. So it is, in some sense, formally stronger than the Lee-Louboutin. It's not a coincidence if we recovered all the values for which they proved the result. But I mean, there are a lot more cases when the rank is 2 without those two conditions. I have included a comment. I mean, if A is congruent to 1 or 0 modulo 4, then the class number is always even. Sorry, always even, except when A equals 1 or 5. These are the exceptions. The reason for that is that when you take the extension of L by the square root of the unit epsilon 2, then it is an unramified extension. So, and it is trivial for A equals 1 and 5, but it's not trivial. It's a true quadratic extension in all the other cases. So it gives, by class field number theory, you get that the class number is divisible by 2. So that's about all I wanted to explain on the comparison of the results. So the link between those cubic fields is via the two descent. Now I want to comment about the other values. What happens when the rank is not 2? And does this occurs often? Well, the thing we can prove, and that is not very difficult, is that actually there are infinitely many values for which the criterion does not apply. So precisely, we can write infinite families, parametric families, for which the rank is at least 3, and there are other integral points. The way to do that actually is not difficult. You have to use a bit of geometry. So for example, we look at, well, this equation y squared plus y equals x cubed minus a square x. Instead of looking at it with a fixed, we look at it as the equation defining a surface in the affine space of dimension 3. It's a cubic surface. It has lines on it, so you can parameterize it over Q. So we write down parameterization and then choose the parameters so that all the values are integers. And this is how I devise this. So for the A's that are of the form 4m4 plus 8m cubed plus 6m squared plus 4m plus 1, there's always rank at least 3. And always some extra integral points. I didn't write D, but we could write the formula. So I have the first example. I mean, when you take m equals 1, you find a equals 23. So there we did a computer search, and we found that the rank is 4. And there are actually 14 solutions to the initial problem. So 14 pairs, so actually 17 pairs of integral points, 3 of them trivial. That's one example. I will give the full list in the next slide. For A equals, that's the highest rank we found among these curves. Then there's a lot more integral points. There's 37 pairs of integral points. So I give those numbers to say that, I mean, when the rank is not 2, there can be a lot more integral points. It seems that it's very difficult to find a general theory for it. So I'll give the numerical example of this A equals 23. So these are the list of integral points. Of course, I have given that each time only one point in the pair, the one with y positive. So the 3 largest are the standard solution, the one given that were already found by Lee and Louboutin. But you notice that some of them, some of the others are fairly large also. So they would be difficult to find by a direct search. Luckily, we have much better algorithm to find integral points. So let's say for any the integral solution seems out of reach. It's too complicated. So let's now concentrate on the proof. Well, the sketch of proof of theorem B and theorem C. So the main tool to prove theorem C. So theorem C, I remind you, is the index of the saturation of the trivial subgroup with the trivial subgroup. So we do this by using Néron-Tate heights and computing essentially Néron-Tate heights. So the main features of the Néron-Tate height. First, well, let's I recall that the naive height of a rational point is essentially the maximum of the numerator and denominator of its x coordinate. So in our context, it's natural to take 1/2 of the log, but that's not that important. Well, it's important to take, it's a logarithmic height. That point is important. Then the Néron-Tate height is a quadratic function that is almost equal to h. You only have to modify it slightly, the naive height, and you get a quadratic function. So with this quadratic function, you can define a scalar product, and you can define the regulator of a bunch of points is just the Graham determinant of the scalar product of the points. So that's for the global Néron-Tate height. There is also a canonical decomposition into local heights. So there I will give formulas. Mainly, I don't expect you to read all the formulas, but the idea is that those local terms are fairly explicit. So one of them is not too difficult to understand. It's a formula for the local height at a prime number p. So I'll take as a hypothesis the point Q is non-singular modulo p. That is when you, of course, the equation of the elliptic curve is non-singular by definition. But when you reduce modulo p exactly when p divides a discriminant, the curve is singular. So the point Q could be that singular point. So you assume that it's not the case. Then there's a neat formula, lambda p of Q is a very explicit thing. And actually, I will only use it for integral points that are non-singular modulo p. So the first term disappears. So the local height is just the order of the discriminant times log p divided by 2. So when you sum all the p's, what you get is log delta over 12. That's the main point. Now, the function at the Archimedean place, I have written the formula. I don't expect you to analyze it if you've never seen it. What I will just use is that it's a very explicit, complicated, but explicit real analytic function. So we can write estimates if we are courageous enough. We can write estimates, explicit estimates for this term. So with this, we can prove the following. So this page more or less gives the proof of theorem C. So the first thing is that, well, we can essentially compute up to a very small error the Néron-Tate height of our trivial points. So we get log delta over 12, as I explained, plus the Archimedean contribution. So we have to analyze what is this Archimedean contribution. That's a bit complicated. And what we end up is that, well, the height of the point P1, P2, P3 is log A over 2 plus 0 or log 2 over 4, a constant, and times a term that goes to 0 with A. So we get a very precise estimate for those heights, and hence for the scalar product of the 2 points. And hence also for the regulator, we just have to plug in the formula. It's just elementary algebra to do this. So I have not written the remainder term, but the main term is for the regulator is 3/16 log a square. That's the important feature. Now, that's where the little gamma comes in, using the decomposition into local heights, and there I have to use the formula for the even that's still true for the points that are singular modulo p. We found that the height of a point has to be at least this quantity. C naught is, of course, is a constant, an explicit constant that I have not written up on the slide. Now, with those two estimates, we can actually prove theorem C. Well, first, we use Minkowski's geometry of numbers. Is that the regulator of a volume of a lattice is essentially the product of the two minimal generators. So if you write this, you end up that this is at least 3/4 the product of two. I mean, there are two generators that you get this inequality. So you get inequalities that I wrote at the lower bound for the regulator of T bar. So you get something that is log a square and some factor. So when you compare this with the regulator of P1 and P2, you end up, well, the index that you want to compute, of course, is the square root of the quotient of the two regulators. That's elementary. And so with those inequalities, you end up showing that it's bounded by this quantity. It's just a direct calculation. And of course, each time we write explicit constants to keep track of things. Now, suppose say that gamma is 1/3, then what it shows is that the index is smaller than 2 plus a very small quantity. We had to add an algebraic argument to show that the index is always odd, except for a equals 4. We know it's equal to 2. And that gives the proof of theorem C, because if the index is smaller than 2 plus a little thing, it's strictly smaller than 3. And if it's odd, then it's equal to 1. That's the proof. So that's the proof of theorem C. So I will be a bit short of time to explain the proof of theorem B. Well, I will give part of it. So what we do is, well, we split in classes modulo 2t the points. So we will first prove that if we consider the translate of by P1 or by P1 plus P2 of 2t, that it points. That's the argument is purely algebraic. The first lemma is you reduce modulo A, your points. Now, if you reduce modulo A, of course, P1 is equal to P2 and is of order 3. It's the Fermat curves. So what you end up is that any integral point will have its x coordinate divisible by A. Now, if we look at the real points, it has two components. Well, one that is compact. Well, that's sort of a circle. The other one, well, that's compact if you add the point at infinity, not compact otherwise. And so the compact component corresponds to x that is contained between the two roots of the x equation. now the two E1 and E2, it's elementary, it's almost minus a and almost 0. So this means that an integral value has to be between minus a and 0. But it's divisible by, if it's divisible by a, then it is minus a or 0. That means it's one of the trivial points. So that's the proof of this part. The second fact is we look at doubles. We'll show that the doubles are the only one that you expect. So that's by looking at the duplication formula that I have written. And the argument goes as follows. So all the points in the trivial group are non-singular modulo p, because the point p1 and p2 are non-singular modulo p, and something that's stable by the group law. So if 2q is integral, then the point q has to be integral. And looking at the equation, we see that 2y plus 1 has to divide 3x squared minus a squared. Now, if some prime divides 2y plus 1, so it would have to divide the 2, and then the point would be singular. But that's not the case. Therefore, I mean, there's no prime that divides 2y plus 1, and therefore 2y plus 1 is plus or minus 1, that's elementary. And therefore you get that the y coordinate is 0 or minus 1, so you get the 3 points that you expect. So that's the argument. Now I have used all my time, so I will just mention that to prove the remaining case is much more complicated. There's no, well, we didn't find any simple argument like this. So we use the theory of elliptic logarithm and linear forms in elliptic logarithm. So that's a lot more important, it's a lot more analysis. And the thing that we managed to prove for that is that for A large enough, the only points are the points we expect. And we need to then do a lot of computer computations to treat the remaining cases. There's a finite set of A's, and the multiples are bounded in terms of A. So there's only a finite number of verification to do. But the number is so large that you need to do it in a more clever way. Otherwise, it would be impossible to check all cases. So I prepared some details of the analysis of elliptic logarithm, but I will stop here.
Okay, thank you very much, Marc. This is really, you are always a pleasure to hear you. Let's see if there is questions and comments. Maybe Mateus can help me here also.
Hey, Marc?
Yes.
Yes.
Yes, since I'm in full screen, I can't look at the chat. So if there's any questions in the chat, you can perhaps read them.
Yes, I don't see also. Well, if you want to, if there's no comments and questions, we can go over, if you want to look at your final slides or things like this.
Oh, okay. So how do we do that? So there says integrals, and so I have written here the formula for the explicit formula for the elliptic logarithm. So the elliptic logarithm, I mean, you know that the curve is isomorphic to C modulo a lattice. So it's actually a map that goes the other way, that to a point sends a complex point, which you call the logarithm. And I will look, of course, only at real points. And so the formula is the following. So essentially, we will not need really to look at points that are not on the neutral component. But for those points upstairs, the elliptic logarithm is the integral from the x coordinate to infinity of this 1 over square root of the cubic polynomials. So a very elementary lemma is that if xq is just a little bit large enough, then this lq is essentially 1 over the square root of xq. So if I take the logarithm of the elliptic logarithm, it is essentially 1/2 of log of xq. Now, if q is integral, then this is essentially the Néron-Tate height, as I explained. So we have this. So we get an important inequality, which reads like this. If the point q is m1 p1 plus m2 p2, and is integral, that's the case we're interested, then I just write the formula for the Néron-Tate height. And what we get is this quadratic form in M1 and M2 times log A with a minus sign. Of course, I have not written, you have to write all the remainder terms. What I mean is the remainder is small. So you can, in the first approach, you can forget it. Now we look at integral points. Well, this is quite important with M1 even and M2 odd. It doesn't work out otherwise, but it's good because it's exactly the point that we need to look at. Then we can look, the logarithm of 2p1 is quite small. It's bounded by a minus 2. And LP2 is essentially sort of a torsion point of order 2 plus a remainder term also in O of A minus 2. And the first period, when you compute it, is a constant over square root of A plus a remainder term. So the very nice thing is that when you write the linear form of logarithm that you want to find a nice lower bound for it, then you can write it. I have written the 2m0 minus m2 in red because this number is odd. So it's at least 1. That's the classical Liouville inequality. And the remainder term, well, is small because, well, I have written on the first slide that the theory of linear forms in elliptic logarithm, the machinery, if you write all the computation, well, it gives a proof of Siegel's theorem. It gives a bound for M1 and M2. And the bound you obtain is a power of log. Let's forget about what power, it's a power of log. So if I plug this in, capital M is bounded by a power of log. So certainly M is smaller than CA to the power 3/2, at least if A is large enough. And so you obtain actually this linear form of logarithm, it is actually 1/2 of the thing written in red. So if you put all this together, you obtain an inequality that reads like this. So A has to be large enough for this inequality to be true. You have a constant times this quadratic form in M, but with a minus sign, times log A plus a remainder term. Now, this quadratic form is non-zero as soon as you take M1 and M2 different from 0 plus or minus 1. That is exactly the point that we already know are integral. So what we get, at least if A is large enough again to kill the remainder term, is that this inequality is impossible. And that finishes the proof. So this sort of analytic estimates, they prove that you have only the expected integral points, at least if A is large enough. Then you have to work more and with computers to do the other cases. So that's basically the sketch of proofs that I wanted to present. I had just 2 questions, and then we do not know there are infinitely many values for which the rank is 2. There are, I mean, all the known heuristics proves that, but there are heuristic, for example, using Birch-Swinson-Dyer conjecture or this kind of thing. But it would be nice to have a direct proof of it, but we don't know the answer. And of course, we don't know in general what would be the proportion with rank 2, 3, 4, etc. There is an intriguing thing that there seem to be a lot of these curves have rank 4. But it's not clear if because we have considered only A smaller than 400, or if really there's a proportion that is unclear. It's an interesting question. So thanks for allowing me to finish the.
Yeah, what was my interest also, my personal interest, to have everything recorded, you know, all the slides recorded. Well, we are basically out of time. So we thank again Professor Marc Hindry for this wonderful lecture. And I would like